Hi all. So in this video we'll be seeing about the home node. So yeah, let us start with a quick introduction and what are the fundamentals of the home node. So imagine you're designing the processor inside a modern smartphone. At first glance, it may seem like the CPU simply reads the data from the memory, performs calculations, and writes the results back. But today's system on chip or SAW is much more far complex than that. Instead of a single processor, modern SoCs contain multiple CPU cores, GPUs, AI accelerators, DSPs, image processors, and many other intelligent hardware blocks. All of these components need to access the memory, often at the very same time. Now, imagine that one CPU core reads variable from the memory and stores in its local cache. At exactly the same time, another CPU core also reads the same variable into its own cache. At this moment, both processors have identical copies of the data. Everything seems perfectly fine. But what happens if one processor modifies the data? Suppose CPU1 changes the value of from 100 to 200 and CPU1 has the latest version inside its cache. However, CPU2 still has the old value 100 because it has no idea that another processor updated it. If CPU2 later reads its cache copy, it will use outdated information. This can lead to software crashes, incorrect calculations, corrupted files, or unpredictable system behavior. This challenge is known as cache coherency, and solving it efficiently is one of the most important responsibilities in the modern processor design. That is exactly where the home harm coherent hub interface or the chai protocol comes into picture. Chai was developed to provide a high performance, scalable cache coherency protocol for modern multi-core processors. Unlike older bus-based protocols, Chai is packet-based, highly parallel, capable of supporting dozens or even hundreds of core and devices into a large SoC. At the center of this entire system is one incredibly important component known as the home node. You can think of the home node as a manager of memory ownership. It doesn't perform calculations like a CPU, and it doesn't permanently store application data like DRAM. Instead, it acts as the intelligent coordinator that always knows who owns each cache lane and what should happen whenever someone wants to read or modify it. To understand this better, let's imagine a simple real world example. Suppose five engineers are working together on the same project document stored in a Google Docs. If everyone downloads a local copy onto their laptop and starts making changes independently, very quickly different versions of the document will exist. One engineer changes the introduction, another edits the conclusion, while someone else corrects spelling mistakes. Soon nobody knows which copy is the latest. Instead, cloud collaboration solves this problem by maintaining one authoritative version and synchronizing updates between all the users. The home node performs a very similar role inside this process. Every processor cache is like the one engineer's laptop. Memory is like the cloud storage. The home node becomes a collaboration server that always knows where the latest copy resides. Whenever a processor requests the data, the home node decides where the data should come from. Should it be read directly from the memory? Should it be fetched from another processor's cache? Should another cache first inherit its stale copy? Should ownership be transferred? The home node makes all of these decisions automatically. Without it, every processor would have to communicate directly with every other processor, creating enormous complexity. Now, let us understand where the home node actually sits inside a chip-based system. Imagine a SOC with four CPU cores, one GPU, and a memory controller. Each CPU has its own private L1 cache. Several CPUs may share an L2 cache. Eventually, all memory accesses move through the coherent interconnect. Inside this interconnect resides a home node. Every coherent request eventually reaches the home node before the final decision is made. This is why the home node is often described as the owner of the address space. Notice that I didn't say it owns the data. Instead, it owns the responsibility for managing that address. That distinction is extremely important. Suppose the address 1000 exists inside the system. The home node doesn't necessarily store the contents of that address. Instead, it stores information about that address. For example, who currently owns it? Which processor have clean copies? Does anyone have a modified version? Should future requests go to the memory or another cache? All of this information is known as the directory information. Think of it like the catalog inside a library. The catalog does not contain the book themselves, instead, it tells you where exactly every book is located. Similarly, the home node maintains information about where every cache line currently exists. Now, let's look at the different components inside the chai protocol. The first component is the request node, often abbreviated as a RM. A request node is any component capable of initiating memory transactions. Most commonly, CPU cores act as the request nodes. Software executes a load instruction or a store instruction. The processor generates the request. The request travels to the home node. The next component is a snoop node or SN. A snoop node is responsible for receiving snoop requests. Another processor may have a valid cache copy. The home node sends snoop messages to verify or invalidate that copy. Finally comes the home node itself. It sits in the middle and coordinates communication between request nodes, snoop nodes, and memory. Notice something very interesting here. The home node doesn't blindly forward every request to the DRAM. Doing so would waste both the bandwidth and the power. Instead, first checks whether another processor already has the required data. Suppose CPU 3 has a modified cache line only a few nanoseconds ago. Latest version hasn't been yet written back to the memory. If the CPU 1 requests the same cache line, reading from memory would return old information. Instead, the home node detects that the CPU 3 owns the latest copy. It sends a snoop request to the CPU 3. CPU 3 supplies the newest data directly. This technique is called cache to cache transfer, and it is one of the reasons Chai achieves excellent performance. By avoiding unnecessary DRAM accesses, latency decreases significantly. Power consumption also reduces because expensive memory accesses occur less frequently. This intelligent routing of data is one of the biggest jobs performed by the home node. Another major responsibility is the ownership management. Every cache line inside the system has an ownership status. Sometimes multiple processors may take a shadow read-only copy. Sometimes exactly one processor owns a modified version. Sometimes the line exists only in memory. The home node continuously tracks these ownership changes. When our ownership needs to move from one processor to another, home node ensures that the transition happens correctly. Imagine a relay race. Only one runner can hold the baton at a time. Before the next runner starts running, the baton must be handed over safely. The home node acts like the race official who ensures that only one athlete owns the baton at any moment. Without this coordination, two processors could simultaneously believe they own the latest copy, leading to severe coherency violations. As processors become more powerful and the number of cores continuously increasing, maintaining cache coherency becomes exponentially more difficult. This is why modern protocols like Chai rely on sophisticated directory based management rather than simple broadcasting. Instead of asking every processor about every cache line, the home node already knows exactly who needs to participate. This dramatically reduces unnecessary traffic across the internet. It improves the scalability, it lowers the power consumption, it enables today's high performance process to maintain coherency across dozens of core efficiently. So, in the next part of the series, we'll dive deeper into the internal architecture of the home node. We'll explore how the directory works, how read requests are performed processed step by step, and how the home node decides whether data should come from the memory or from another process cache. Once you understand that transaction flow, the entire chai protocol becomes so much easier to visualize. Thank you.